transformations, kind of moving things up and down, sideways, kind of stretching them out, flipping them upside down, and that kind of thing. So you might want your graphing calculator, just because it might be handy to graph some of these here and there so you can see the transformations for real. So transformations relates, transformations relates a bit to year 11 and 10 symmetry. So some of the phrases that you'll be using are similar to what you would have used in symmetry. So remember back to CIE, GCSE transformations. The types of transformations which relate to this unit are, what was one that kind of like looks like this and starts with T? I think Calvini, you mentioned it the other week.
A translation?
Translations, yeah. So the first one we're talking about is translations, whereby a function is shifted either horizontally, like in the first example, or vertically, like in the second example. So this one's a horizontal. So this one is a horizontal shift. Well, let's say the original function was the one in black. So just x squared, simple x squared function. So that would be y equals x squared. Is the original one. And the shifted function is the red one.
Okay, so y equals x squared.
Ooh. Would be the original one? Yeah, what would be the equation of the red one? Yeah.
Would it plus 2? No, subtract 2.
Minus 2, yeah, y minus 2?
Because it goes the opposite when it's on the x-axis. I just remember from GCSE.
You just remember from GCSE, yeah. It goes in the opposite direction, doesn't it? A horizontal shift. So move 2 units to the right. So it means in the equation, horizontal shift is represented with the x, kind of like, as in like x plus 2, x minus 2. Whereas vertical shift, where in the equation do you see the vertical shift? Not so much in with the x, but with a different term.
And y? Wait, what
Similar?
did you ask? C.
Yeah, C, the constant term. So the vertical shift, you'll see the number in the constant term. It'll be the constant term.
So x squared would
kind
be
of
by itself, and then you would add a.
Yeah, exactly. So this one here, it's a vertical shift. So it appears in the constant term, the vertical shift. How many units kind of roughly did it shift up?
1.
1, yeah. So what would be its equation?
Y equals x squared plus 1?
Yeah, x squared plus 1, yeah. So you see the difference between where you see the vertical shift in the equation and where you see the horizontal shift. The horizontal shift, vertical shift. I didn't finish these things either, did I? A component vector is often used to represent these shifts. For example, minus 4, 7. Remember component vectors are in the form of like x, y.
Yeah.
So in that particular example, that means a horizontal shift. And the vector follows the signs. So if this is a horizontal shift, negative 4, is that to the left or the right?
Right.
Close?
It follows the sign.
It follows the signs. Yeah, so that's what's confusing. In the equation,
What the heck?
yeah, in the equation, it goes against the sign for the horizontal shift and it goes with the sign for the vertical. But in the vector, the vector's saying literally what happens. Not so much what happens in the equation, but literally what happens on the graph.
So in that thingy, it's always exactly what
Yeah.
it's saying, but in the equation it's the opposite for the horizontal.
Yes, exactly. That's a good summary of it all. So in this little component vector form, it's exactly as you see it. So that's 4 units to the left, and what does the 7 mean?
Upwards.
Upwards. Yeah, exactly. Yeah. So it means a horizontal shift, 4 units left. So you don't need to say negative 4 units left, because I've already implied the left. I've already implied the negative by saying left. If I didn't say the word left, you could say a horizontal shift, negative 4 units. That would imply left. But because I've got the word left in there.
So when it's not in the vector, if it says negative 4, it means go to the right form. But if it is in the vector and it says negative 4, it means go to the left.
Yeah, like if it's in the equation form for horizontal shift. But for vertical shift, it follows the sign. So if it's plus 1 in the vertical shift, it means it's gone up 1.
Okay.
If it's minus 1, it's only the horizontal shift in the equation that it goes against the sign. Oh yeah, and vertical 7 units upwards. The last one has had a bit of both happening. sort of the last example here. So it's had a horizontal and a vertical shift. So what would be its equation?
Would it be y equals bracket x squared minus or bracket minus 2 x plus x minus 4 squared. Y minus 4 squared. Oh, it's all squared together?
Yeah.
Oh, it is. Oh, just oh my god.
Okay, I didn't do that. I'm glad your eyes saw that.
And then negative 2. Yeah, you
Yeah, you're at negative 2. Sarah's got it. So yeah, 4 units to the right. So it shifted from the vertex. We kind of use the vertex, don't we, as our little way of seeing it. Because it's not dilated at all, so there's kind of no stretch or anything like that happening. So there's no extra number in front of the x squared. Or in front of the
I
bracket.
said this and a tap would just be
So it's the same width. It's the same shape, it's just shifted vertically and horizontally. So we've got our horizontal shift and our vertical shift. So you might want to add in a little note about that. So this is the horizontal, this is the vertical.
Someone who loves.
So horizontal and vertical translations are pretty nice and easy. They're the ones you hope to get. These ones can be a bit awkward. Yeah, rotations. Oh, hang on. Is it rotations or is it?
Reflection.
Reflection, I meant to say, yeah, sorry. Yeah, there is a thing called rotations, but you don't see it so much in this particular unit. The one you see a lot, though, is you do see reflections. But you're right, there is such a transformation.
What are we doing factors? What?
We can do vectors, normally here we can do vectors in IB2.
Didn't we do that? Denmark.
Yeah. Nah, we tend to do it formally in IB2. Vectors. So reflections, whereby a function's mirror image can be sketched. These always include a line of reflection. Yeah. Something's wrong. So it always includes a line of reflection. What was I meaning by these pictures? Okay, so alright, so if this was
Now, how do you know it reflects on the x axis and then the 3 reflects on the y?
oh, well done. Okay, yep. I'm glad you saw that because I forgot what this was. So here's the original function. So here's the original function. Chiesa pointed out that the figure 2 is the original one, but reflected in the x-axis. So sometimes they're reflected in x-axis. It could be reflected in any line, though. It could be reflected in y equals x, or the diagonal line. It could be reflected in y equals 1 or x equals 3. So it's, I would say, it's being reflected in the x-axis. What's the equation of the x-axis, by the way?
Would the equation for the axis? Y
Y
equals 0?
Yeah, good, yeah, y equals 0. Because they might not say x-axis, they might say y equals 0. And Chiesa's noticed that the second one has been reflected in which axis? X or y, yeah.
Oh,
Yeah, x equals 0. Yeah, in the line x equals 0. So it's been reflected in the line in x equals 0 or the y-axis. So it's being reflected.
How do you reflect
Like say, yeah. So say if it was the last one, yeah, draw the line of reflection just like Calvina said. That's kind of a handy thing to do. And then see, I would say this little point
where's
here
the line of reflection?
has to appear equidistant, but over here. Equidistant kind of
and then
thing.
the other one's the same?
Yeah, and this little point here has to be equidistant, but over here.
Okay.
What are you saying, Miss Lily?
Just how to use the mirror images to reflect it.
So the line of symmetry is the y-axis.
Yeah, in this particular example they were. So if it was the y-axis, the line of symmetry, so you would kind of like, the way you could reflect it is you could take a point and see it distance from the line of reflection has to be equidistant. So it's like
To the other side.
Yeah, it's like
Yeah.
1 2/3, so go across 1 2/3. And then this point is kind of like 3 and a bit units over. So from the other thing it has to be 3 and a bit units over. And the vertex, where would the vertex appear?
Yeah, but why are you reflecting it that way?
Just if the question was reflected in the y-axis.
So it means go that way.
Yeah, so we're flipping it this way.
Got you.
Where this one has been flipped that way. instead.
Yeah, that way.
So where would the vertex be for this one?
It'll be, that one's 1, 2, 3, 4 units down, so it'll be 4 units up there.
Yeah.
Oh no, you're reading it that way.
Yeah, kind of like over there. And then you would kind of do a rough sketch. Oh, and also the intercepts as well. Intercepts are another thing you could have sketched. So this intercept is at 3, so then over here it would be -3. Confusing with all these dots, isn't it? And then this intercept here is at 1, so that one, -1, that one would be +1. And then you could kind of just, oh, and it's kind of also note at another point is C, Isabella, on the y-axis. You would have the same, the reflective one would be there too.
Yes.
See what crosses the y-axis. And then you would just do a dotty sketch like that.
Okay.
And then just sort of look at it and think, does it make sense?
Wait, so my like diagram is very ugly. Let's look at the work.
Yes. Yeah, like if we look for key points and the general shape kind of thing. A few key points and the general shape is what we look at. So it's kind of going to be tricky to do. I noticed you guys did it in topic assignment 1, which we'll get back today as well. You guys did a few reflections.
Oh, that was that bad. That was a struggle. That was me.
So done with that one. What's the other things that we said? Yeah, stretches, yeah. Stretches. Which generally in this course you see stretches that are either horizontal or vertical kind of stretches.
Scale factor.
Yeah, these include a scale factor. Yeah.
Oh, I didn't even turn off. What do you mean?
These include a scale factor K.
I'm gonna eat my lunch at least.
So let's say the original one. What kind of function is this one here?
Absolute. No, it's not.
Yeah, you're
Oh,
right.
it is.
Yeah. The absolute value. Yeah.
Oh.
Just a reminder. Absolute value function. Absolute value function. Let's say the original one was the one in black. The y equals absolute value of x. And the stretched one, the translate or the transformed one, would be the one in red. So what would be the scale factor there? You can sort of see it from here.
Wait, it goes
So
from.
it's handy if they give you the equation.
It goes from. Which one's the original?
Yeah, what's the significance of that too? What does that mean?
Yeah, what is it?
Well, Miss Veronica, can you raise your
Let's say the original one is this one.
This is the original. This is the OG.
Yeah, the line I just drew is really messy.
Yeah.
Yeah.
So then how's the scale factor too? It's getting. Yeah, how? Why is it like that?
I say no.
Well, it's also just from the equations.
No, but how does it go from like here to here?
Because we were taught that like when you stretch something, you only stretch it in one axis.
Oh,
So,
yeah,
like,
yeah.
if you're stretching from here, it can only go to like there. But if you're stretching vertically, you can go like that. So like.
So what? So it might have an invariant. More so would have an
confused
invariant.
as to how you
So what would be the invariant?
Yeah, I'm so confused. What
I
did you
don't
know?
know because it's stretching in both directions.
It's kind of. Would you agree? It's sketching away from the x-axis to
Yeah.
some
So
extent. Yeah. So maybe an invariant x-axis.
If it's a like a 2, why doesn't it get wider? Why does it make
Oh, I get it, because you do the thing where you're on the axis and then you count like 1, 2, and then if it's scale factor 2 times that by 2, so then you go 1, 2, 3, 4.
Yes, that's right.
Yeah,
So
can
each
you-
point.
yeah.
So the 2 makes its y value double what it was. So the original one, its y value was
Negative.
let's say it's 2. So now on the stretched one, its y value will be twice as high. So it's gone up 2 units here to this point, just so the video sees what I'm talking about.
Oh, so it's only shorter
So now-
because you don't have those part of that part of the scale. Like it's not a full, like it doesn't go to there.
Yeah, exactly. Like it will keep going out.
Okay.
Yeah,
it
yeah.
just don't have difference.
Yeah, exactly. Yeah. So
If
that's
it was at
yeah.
this one,
So it would eventually get wider and
so
wider.
the y value was 5, the original y value was 5,
Hmm.
then the new one will be 10.
Yeah.
So if
For that
it's
extra-
negative 2, they'll go the opposite.
Yeah, it would
It'll
flip
get
upside
wider.
down. Good. Oh, if it was, yeah, that's a good point. What would make it? What kind of scale would make it wider? -2 would make it flip upside down. Yeah, half. So a value between 0 and 1 would make it wider. Because when you think of it, if it was a half mod x,
Yeah.
then instead of being at 2, it would suddenly be at 1. Each point will have been half of what it was, and then it would be wider. So if it was a half x, a half mod x at the front, then it's going to make all the y values half as high as they were. to the same x value, and it'll get wider. Yeah, sure thing. Yeah. So I tend not to so much call these like the number 2 a scale factor. I tend to call it a dilation factor. You'll hear me call it a dilation factor more so. 2 mod x, I'd call 2 the dilation factor. Because remember, you know how your pupils dilate according to the amount of light that's in the room? They get bigger and smaller. So for me, I see it more as like a dilation. I think the word dilation is a bit better to use. Because dilating, you're making it kind of skinnier, you're making it wider. To make it skinnier, you make the number you're multiplying the function by, like the a value basically, the front, you make it bigger, like greater than 1. Because that's going to make all the y values be higher. So for this x value, its y value is double. Then for this x value, its y value is double. And if you halve it, then they get lower. So then they'll become wider instead.
Miss Renee, can we make that into the middle?
Yeah. So I'll say the dilation factor equals 2. Dilation factor equals 2 for this particular one, which means the graph becomes narrower. Narrower than the original function, which was y equals mod x. So the dilation factor equals 2, which means the graph is narrower than mod x. Make a note. If the dilation factor was between 0 and 1,
I don't have that much space.
Oh, exactly.
e.g. a half mod x. So for example, if the function was a half mod x, or like a third or something like that, the graph would be wider. Because all its y values are half of what they used to be. Would be wider than, you don't need to write all this if you don't want. Whatever makes sense to you. So here, this little red example, the dilation factor was 2, which means the graph became narrower because all the y values are now twice as high as they were. But if the dilation factor was a half, like they mentioned, then the graph would be wider because all the y values, the heights of each point, will be half of what they were.
Wait, so this is for every single graph ever?
Yeah. And notice where does the dilation factor, where do you see it in the equation, kind of?
It's before the after.
Yeah, it's kind of like like the coefficient sort of x almost, or the coefficient at the front.
So if it's negative, it gets reflected.
Yeah, that's a good point. If it was negative, it would be similar to the one here. It would be reflected in this one here, reflected in the x-axis.
So if it was negative 2x, it would get narrower and then reflect.
Yeah, would be flipped upside down. So negative 2x would be like the red one, but it would be kind of going downwards instead.
Oh, wait.
Yeah, it would be just as wide.
Negative means it reflects in the white blue 0 line. Is that really, yeah?
So we could do an example on this one of a negative one. Like, what's the original one? Which one? The original one is kind of like the dark blue. And we've got a dilation factor of 2 in the light blue one, and dilation factor of a half in the orange one. So if we did, for example, let's do in red, or whatever color you want to use, let's do another one, y equals negative, you don't have any space? Y equals negative 2x squared. How do they put it in brackets? So it's kind of like the light blue one, but flipped upside down. So that should be a negative at the front there. Okay, there you go. So what that's meant to be y equals negative. It's the negative of this one. I just tried to make the negative of that, just to point out that it would flip upside down. If you put the negative at the front in the dilation factor.
I know that one. No, that.
It's like,
You know what?
Is it always that it reflects the x-axis?
Okay, yeah, now I know.
Yeah, in those cases, yeah.
I just
When
need
its
to do it with
reflections
the
are reflected, it
Oh, I didn't
Wait, no,
How do you know
which
that?
one's reflected? Do they say reflected in
That's a good point. Yep.
X?
So if it was negative fx, if it was negative fx, negative fx means it's being reflected like this one in the x-axis. To reflect it in the y-axis, it would be f of negative x. That's a good question. Because all the x values got reversed. So notice in the third one here, all the x values got reversed. And in the second one, all the y values got reversed.
What if it was a line?
So that would be kind of things.
Y equals 2.
Oh, and if it was y equals 2, that would be normally a line like through here. So if it was reflected in the x-axis,
Wait, isn't it if y equals 0, wouldn't it be a horizontal line? Oh yes, never mind, go ahead.
so yeah, if we're talking about what the line, if, for example, if it was a constant function like y equals 2, if it was reflected in the green y-axis, it would be the same line, wouldn't it? Because you flip everything over, it'll still be a horizontal line through there.
Oh.
But if you reflected it in the x-axis, it'll be down here suddenly. It would be like a mirror image, it would flip. If it was reflected in the x-axis,
Yeah, it will flip.
it would suddenly be y equals minus 2.
Okay, yeah.
But if it was
Yeah.
if it was reflected in the green y-axis, then it would still stay y equals 2 because all those points would just flip over
Yeah.
that way.
Okay, that makes sense.
So that was just because Isabella just asked about an example like that.
But for me, I don't understand when we jump here.
Yeah. Okay. You mean which one?
The parabola down below.
Oh, down below.
The
Sure.
quadrats.
Yeah. Oh, it has scrolled down. Cool. So which bit? This bit here?
Mm-hmm.
What's that little question? Just about the red one that I just did?
Okay, so why is it? So before it was y equals x squared, and now it's 2x. So that means it comes in more.
Yeah, it's more narrow.
So that means when y was 2, now it's going to be 4.
Yeah, so if see this one, yeah, exactly. Because, and how did you get that it was going to be 4 times as high? Oh, no, hang on, it's not. That's a good point. Is it like as 2x all squared, what does that expand to become? 4x squared, doesn't it?
That's why on the graph where it's at 1, now it's at 4.
Yeah, that's a
Okay.
good point. Yeah, so
Okay.
that's well noted actually, yeah. Because this thing here, I don't know why they wrote it like that. I would have written it y equals 4x squared. 4x squared. So the dilation factor is actually 4, because 2x in bracket squared is 4x squared. And so Krista's noticed that on the original one, when y was 1, it was at 2, but now when y was 1, it's going to be up at 8. It's going to be 4 times as high.
Oh no, it wouldn't be at 8, would it just be at 4? Because 1 times 4 is 8. I mean 1 times 4 is 4.
Oh, notice that it's y value. Oh, I was reading it wrong too. So at 1, the original one's y value is at 1. Sorry, yeah, I was reading the graph wrong. So the next one is at 4. Yep, good. I was reading the graph wrong. Yep, because at 1, the original one, the dark blue one, is at 1. So on the 4x squared one, the dilated one, it's going to be up at 4. 4 times as high. Well noted.
Is it a lump good?
And did you also notice 0.5x squared? That's in brackets too. So what would that be? 0.5x squared when you expand that?
0.25.
Yeah, 0.25x squared. So it's a quarter now, isn't it? So that technically is actually y equals 0.25x squared when it's expanded. So that's why you notice that when it was 1, it's now at a quarter. So at x equals 1 when it was at 1 on the original, it's now at a quarter. Can't draw it on the exact spot. So really you need the expanded form to see the dilation factor to some extent. About the one that we were just talking about. So notice that here's the original one, the dark blue one. A good coordinate to look at is coordinate 1 and 1. So there is a coordinate at x equals 1, y equals 1. So notice for the dilated one, 4x squared.
Oh, so these are all talking about x value?
Yeah, at x equals 1, its y value is now 4 times as high. So at x equals 1, its y value is now up at 4 instead of 1. And for the widened one, y equals 0.25x squared, at x equals 1, instead of it being at 1, it's down at a quarter of what it was. And for this one, negative 2x squared, which would be negative 4x squared, when it's expanded, it'll be just like the light blue one, but flipped upside down. Confusing stuff. Any more questions about? Yeah, keep asking.
So if you look at on the orange one,
Yeah.
it's x equals 2, right?
Yeah.
So then quarter would be a half.
Oh, the orange one is already a quartered, like it's already been widened. The original one's a dark blue one.
Yeah.
The middle one, yeah. So let's look at the original one to start with. So at x equals 2, would you agree that y is 4? On the original dark blue one?
Oh, yeah.
Yeah, so the original one's a dark blue one. So then at x equals 2 on the orange one, it'll be a quarter as high. A quarter the height of the original.
Yeah.
Yeah, because the original is just x squared. And on the blue one, the light blue one, the 4x squared, it should be 4 times as high as the original. So it'll be up at 16. And that's why we can't see it, because it goes beyond the scale, of course. Like Lauren was saying, the scale doesn't show it going all the way up. Crazy stuff. Translation. But yeah, that's a good little thing to note up here. You know what we're talking about? The instruction to reflect in the x-axis, the instruction would be sketch negative f of x, means flip it upside down. Make all the y values and the from the bottom become the top ones. Make all the y values at the top become the bottom ones. And the instruction for a reflection in the y-axis would be f of negative x, meaning the x's swap over. All the positives move over here, and all the negatives move over here, like what happened between these two. And this thing happened from that one. That was the original. We flipped it. So that's the instruction for reflection in the x-axis. This would be an instruction for a reflection in the y-axis. All the x's swap over. Here all the y's swap over. So that's something you might want to notice. I might get rid of that because that's confusing, having that there. I think we're ready for the next page, are we? Any questions? Yep, next page. Well, you're looking restless. I made a typo. Can you see my typo? Can anyone see my typo? Isabella, where's my typo? What do I mean to write? Certain notation tends to be used. Certain notation tends to be used in exams to instruct you to do these transformations. Like these kind of things. This is like the way they'll instruct you. They'll say, sketch this or find this kind of thing. Like how we were just talking about a bit then on the previous page. So what am I asking you to do? If we consider the original function to be f of x, sorry, Isabella, then state what kind of transformations these would be. Yes, Isabella? Horizontal shift? Yeah. Yeah, good. How many units?
2.
Yeah, good. So a horizontal shift, or you can say translation if you want, horizontal translation, shift, whatever you want to use. 2 units to the left, good. Yeah, because it's going against the sign. Here it's saying positive 2. Horizontal shift is in the opposite direction to the way it's given in the equation. It's in the same direction as the way it's given in a component vector, so, or a column vector, but the opposite direction. Horizontal shift 2 units to the left. Opposite direction to what you see. So we're just going through and trying to state what these would be. How would you say these things in words? So they won't tell you in words to do these kind of shifts. They'll tend to just use these symbols and expect you to realise what they're asking for.
A horizontal shift 1 unit to the right. What?
Oh, similar? It's a reflection, yeah. What kind of reflection? Reflection in the x-axis or the y-axis?
In the y.
Yeah, it's confusing, isn't it? Yeah. A reflection in the y-axis, yeah. Because all the x's have swapped over. So if this was The original one. Then the other one. It's a diagram. I know, I didn't make it very obvious, did I?
The reflection.
What you
What are you trying to show?
It's a reflection. You see how it's big on that side and big on this
Yeah,
side?
yeah,
It's not obvious.
I should have made it a bit more exaggerated. Yeah, so try to make one of them closer to the axis and one of them further from the axis. A bit more than I did. It's not really clear. Oh, yep, the next one is a vertical shift. I'll just keep on banging on about the second one though. The reason why we knew what it was is the x's will swap over. So the x values will swap in the coordinates will swap. So that is a little clue to me that it's a shift across. So the x values will swap over. Is what that is meant to say. Owen, what kind of transformation do you see here? Yep. How many units? Yep, and up or down? Down, yep. So the vertical shift follows what the constant term sign is. So vertical shift, 4 units down. I don't know what that means. So the shape of the graph, it hasn't dilated or anything like that. It hasn't gotten wider or narrower. Everything's just shifted 4 units down. So it's in the constant term that you see the vertical shift. Is that the next baby?
Reflection of the axis.
Yeah, it's a reflection in the x-axis. Because this will make all the y values swap over. Reflection in the x-axis. A little picture to show that. It's a lovely reflection line. Great picture, but still, if that helps draw the picture. So that's what, as I said, this makes the y value swap over. So that's how I tend to remember it. It's like, so in yellow and purple, I've tried to sort of explain. I'm talking about the negative part here. Makes all the y values swap over across the axis. So these parts here are just like how I remember it. You write it how you could remember it. So cool. So that's nice. What about the 3 being shoved out the front? What does that make it do? How will the 3 change the way it looks? It's a stretch, yeah. I call it dilation. It's a stretch. It's a stretch, yeah. Yeah, that's a stretch as well. More like it kind of makes it all come inwards. And I'll just deal with this one first, and then I can also show you. Like, we'll show you by doing a sketch of the F4X one. So 3 effects. I call it a dilation. Dilation with dilation factor 1. If you want to call it scale factor, then use that terminology instead. But dilation factor of 3, sorry. Making the graph, does it make the graph narrower or wider, the 3 effects?
Narrower.
That bit. Making the graph narrower. Now the F4X one is an interesting one. And I might kind of try to demonstrate that with an example. It's a bit crazy, that one. So let's do a regular looking x squared, let's see, minus 4x minus 8. So I've just done a regular little graph, x squared minus 4x minus 8. Ew, is it on a graph? Yep, here it is. I might want to adjust my window a bit. So just so I can see the vertices. I mean the vertex, the more singular one, -20. So you just dilate, just not dilating it, just adjusting the window. So trying to just sort of do an example of this. Oh, graph. So I've just made a quadratic, and it's going to pop up. I'm now going to make a quadratic with this. So, Isabella, how would I enter? So this is, imagine this is my little original one.
Yeah.
And I'm going to now plot a second one, but I'm going to factor the 4 in with the x.
Bracket.
Good, good, good. 4x, yep. Oh, and then notice that the 4x would be here and then a square. Yeah, that's what you meant, yep. And then minus 4.
That bracket kind of important.
Yeah. And then the -8, there's no x there. Yeah, so see, sorry?
So wherever the x, you plug in 4x.
Yeah, it's kind of almost like we're doing a composite function, isn't it?
Okay.
Yeah, so it's like we're doing a function of a function. It's almost like in the original function, we're replacing all the x's with 4x. So instead of x squared, we've got 4x in brackets squared. And then instead of -4x, we've got -4 brackets 4x. And then -8 is just a constant. Do you want to have a, what do you think might have happened to the graph?
It would become more, instead of being like that,
Yeah?
it would be like this. Like it's going to be more narrow. You know what I mean?
Yeah? Yeah, exactly. Yep. And do you think the vertex will be roughly in the same spot?
No.
It's very hard to pick, isn't it? Let's see. So here's the original. Now here's coming our other one. Yeah, so the vertex, so the one part of the vertex changed and one part didn't. Which part changed?
What do you mean? Oh, so the y values get the same.
Yeah, y
The
value
x
stayed the
value
same. Yep, the x value changed. Yeah.
So what part of the equation would be y x value change?
Oh, which part? The fact that we've subbed in 4x
Okay.
instead of x. So let's see if we can rationalize. And what's happened to the x-intercepts?
Change, it come down.
Yeah, by a factor of
4.
4. Yep. So I should have done one that had a more obvious kind of like x-intercept, like, you know, a whole number. So would you say, is this one kind of like a quarter of what it used to be? And is this one like a quarter? It's kind of all shifted inwards, hasn't it?
A quarter.
Quarter. I'm trying to figure out what's the terminology for this kind of stretch.
I don't understand how
The reciprocal scale.
It's probably in the book. I'll just quickly pause this. So this one we call horizontal stretch or compression. This one is a vertical stretch or compression. This one affects the y values and this one affects the x values. So I'll take a little copy of that thing. Where's my little thing to copy? Where's it gone? Snipping tool. Take a little snip of that. So just taking a little snip of this. There you go, put that there. So we'll call this one dilation factor, so this one is a vertical. So this one here, the 3fx, it's a vertical stretch or compress with scale factor 3.
Isn't it a compress and it'll be a stretch if it was a fraction?
Yeah. Yeah, exactly. I suppose compress could be the umbrella term. So with the vertical one, like the 3fx, the scale factor is just the 3. But with the horizontal one, horizontal stretch or compress, the scale factor is 1/4. Because notice that if it was at, for example, if that was at 4, on the compressed version, it's now at 1.
But if it was a stretch, it would be at 4 times 4 b. I mean, it'll be.
Like if it was a quarter. Like if it was f brackets a quarter x.
So then it'll be, instead of be a 4, it'll be a 16.
Yeah, yeah. That'd be further out, yeah.
Well, what is a vertical?
Yeah, so this 3fx, we call it, it's a vertical stretch or compress with a stretch, with a scale factor of 3. This one, it's called, it's a horizontal stretch. You can also call them compression, so I'll put in compress. well, this one is a compression, with scale factor 1/4. Make everything come in narrower. So that's kind of the official terminology that we can use. They were a little bit confusing, those ones. But now we can see some nice words, terminology we can use for this. This little one here, what kind of transformation do you think that is? Getting a bit repetitive. Yep. Translate.
Right along the x-axis.
Yeah, exactly. It's a horizontal translation, 1 unit to the right. Some people say 1 unit in the positive x direction as well. So a simple one is horizontal shift, horizontal translation, say shift, whatever. Horizontal translation, 1 unit to the right. Another way you can say it is a horizontal translation, 1 unit in the positive x direction, meaning 1 unit to the right. If it was to the left, you'd say 1 unit to the negative x direction. That's another way you can say it.
Yeah, that's a good reason you can be against that because
Yeah. How about the next one? Yeah. Yeah, so you can say vertical shift, you can say vertical translation as well, kind of showing you the different ways you can say it. You could say 1 unit in the positive y direction, or you can just say up, it's fine. Just showing you different ways you can express it. Which means 1 unit in the positive y direction. So trying to make it kind of interesting now. If this one's a bit hard to see, you can probably express it in a different way. Would you agree that's the same as 1/5? 1/5 f of x, in case that's easier to see. Yeah, so fx over 5, it's like saying 1/5 of x. That is reflection, translation, stretch. Stretch, yep. Is it a vertical stretch?
Vertical.
Yeah, okay, yeah, sure. Because it's got just a like little coefficient at the front. And what's its scale factor?
1/5.
Yep. Dilation, whatever it is. You could say dilation if you want. Vertical stretch. Or compress. Let's get used to the words. Scale factor. 1/5. Scale factors for the vertical are what you see in the equation. Yeah, we've got multiple transformations going on here.
and then you know.
Ugh. What does a negative do?
Refraction.
In which axis?
X.
Reflection in x-axis. It's all flipped upside down. What does the 2 do?
Stretches.
Yep. What kind of stretch?
Vertical.
Yeah, vertical stretch. Yep.
Wait, vertical stretch meaning gets narrower.
It's narrower, yeah.
And if what is the horizontal stretch? Is there a horizontal stretch in it?
Nah, because there's no number. See, the x doesn't have a coefficient other than 1.
Okay.
Yeah, that's a good point. Yeah, okay. If the x within the function has a coefficient,
But what does that look
vertical stretch with scale factor 2. Yeah, what would it look like? Yep. We'll do a little sketch of it afterwards. What does the 3 do? Horizontal shift. 3 units right. What does 4 do? push your 4 units up. Ugh. Clear, clear. Try to do just a simple one, x squared maybe. So if you want to see that one in action, so if our function was x squared, we'd need -2, and then we'd need x minus 3, wouldn't we? Am I doing this right? I hope so. X minus 3, and I'll need the square, plus 4. So see what I've done is the square would pop up here. So the square would be there, otherwise it would look like that. Let's see how it looks. So it's going to sketch our normal x squared. Here it is. Now it's going to do the transformed one. There you go. So it flipped it. There was no, as Krista mentioned, there was no horizontal stretch at all.
So what would a horizontal stretch look like?
I guess it would, if it was, say, here, instead it was 4x, everything would have gone in, be thinner by a quarter. Everything would have shifted in vertically by a quarter. So these x-intercepts would have been a lot closer together, like this. Oh no, maybe that would move too. And then plus 4, yep, so it's kind of roughly the same thing, except it's been, oh no, it's been dilated though. So notice this one was a bit wider, this one's a bit narrower. So it's a bit narrower. It's flipped upside down, it's moved across and up and all that kind of stuff. I'll take a little snip of that.
Okay, but Miss Lang, I'm still not understanding. I understand what a vertical stretch, I know vertically it will either go like more inward or out more. But I don't understand what a horizontal one would look like.
Yeah, so if there was a horizontal shift component in there, do you want me to
Yes, please.
pop that in here? Let's do one on here. So if there was a horizontal component to it, we would have like a little number here.
Yeah.
So let's do maybe 2x, or will we do 4? Let's do 4, just so it looks different to the other part. 4x minus 3. Oh, I've got to put in a bracket and square it. Does that work? Okay. Okay, let's see what that looks now. If we put in a horizontal stretch in there as well. Here's our original. Try to remember what the other one looked like. I've got it here actually. That's what the other one looked like. Yeah, so what do you notice about the difference between now we've got a horizontal stretch in there? Yeah, everything's coming a bit narrower. I think that thing shifted over a bit too, and everything's a bit narrower. Because our scale factor, what would be the scale factor for the horizontal stretch? So what would be the scale factor for the horizontal stretch I did here? Close?
Oh, wait.
1/4, yeah, 1/4. Because everything got shifted into a quarter of what it was. So it's now a quarter as wide as it was here. So it's a good point. So vertical stretch follows the dilation factor that you see. Horizontal stretch is 1/, the coefficient that we popped here. So 1/4.
What if it was 1/5? What if 1/5 is horizontal?
Okay, so 0.2, do you mean?
Like it would be,
Oh yeah, you want to see if it widens, yep.
if it is, okay, it's a 4, it's 1/4.
Oh damn it. Okay,
You did everything, yeah.
I'll just type it in, yep. 0.25 x, yep, so instead, and then minus 3. Close our brackets. Okay, let's see how that looks.
So it's become wider.
Yeah, wait, yeah, that's our little prediction. Look at it widen out. The vertex has moved right over. So the vertex has shifted right over. It's super, super wide. Did you see that, Isabella? Did you see that? Is that so the vertex has shifted over. The x-intercepts will be much wider apart, and the x-intercepts have shifted over as well. So that's probably the most wacky one, I would say, is the horizontal stretch.
Even if it's like before it gets bigger,
Mm. Yeah, because the dilation factor is now 1/4, which is 4. So our dilation factor in this case is now 4. I mean, our scale factor. Yeah, the scale factor for horizontal stretch is 1/0.25. But for a vertical, it's just 2. But it's 1/, that one, for the horizontal. A bit similar to like how the horizontal one in the shift, in the translation, is the opposite of what we see. The horizontal one in the stretch is 1/, the number that we see. So horizontals are the big wacky ones.
So if we have 4x, if you put 4 right there, we wouldn't say by a factor of 3, we would say by a factor of a quarter.
Yeah, scale factor of a
But
quarter.
if it's at a quarter, we would say by a scale factor of 4.
Yeah, because 1/4 is 4. Yeah. Yeah. Yep.
Get it right.
Yeah, good point. I think so. I think the word dilation's okay. But if you want to, like, play it safe, just say stretch. Horizontal or vertical stretch. Just in case. In Australia, we tend to say dilation a lot. So I kind of had that on my brain. So I'll try to start saying stretch a bit more so you guys get used to it. It's recess.